Salutations, mini mathematicians! We're continuing with Module 7. We're going to be looking at some nonlinear functions that work very similar to the last nonlinear function we were working with absolute value. My computer's plugged in today. Pi's not here to distract me. She's outside enjoying the beautiful weather. So let's get to it. We're working with 7.2b, quadratic functions, and this is going to be part 1. So our purpose in this lesson is to identify a quadratic function from a table, a graph, or an equation, and then be able to graph a quadratic function and apply the function to a real-world situation. So what's really cool is that quadratic functions are very applicable in our everyday life. Whenever you're throwing, bouncing, kicking something, it follows a parabolic motion. So if I kick the soccer ball, it's going to go up, it's going to reach an apex, and then it's going to start to come down, and it's going to have this symmetric shape. If I was up on top of my roof and I decided to throw something off of it, because why not, it's going to also follow this parabolic motion. And even if you're tossing a baseball or a softball, if you're a pitcher over to the batter, that pitch is going to follow a parabolic motion. Playing one of my favorite near and dear sports to my heart, cornhole. That's a parabolic motion. Just sink it into that cornhole, 2 points, what? So if you are out playing some cornhole today, make sure to really use that parabolic motion and what we're talking about today to think about the trajectory of that beanbag. And if you don't know what cornhole is, YouTube it. Be cultured, people. So let's get started on our notes. Okay, so like I said, 7.2b, lesson quadratic functions, part 1. And what we're going to be looking at first is a roller coaster of fun. Roller coaster. Okay, so the Steel Dragon in Japan was built in 2000 and is one of the longest and tallest roller coasters in the world. We're going to use the function h equals 400 minus 16 times the quantity of t squared to determine the height of the Steel Dragon, h, the height, as it falls from its tallest drop. Remember, one of the tallest drops in the world. The variable h represents the height above the ground in feet, and t represents the time the coaster has been falling in seconds. So we're going to create a table of values to determine how long is it going to take the Steel Dragon to reach the bottom from its tallest drop. And we're going to write our data as an ordered pair. So we already did at time 0. So thinking about it, time 0, how high are we off the ground? That's going to be our total foot drop. Ooh, so let's see. Height, I went over the height. I'm substituting in 0 for t. Order of operations, 0 squared is 0. 0 times 16 is 0, and 400 take away 0 is 400. So we are starting 400 feet above the ground. And we're writing as an ordered pair, t comma h, so 0 comma 400. I'm going to do one with you, and we're going to show our work, of course, here. H is equal to, just like they did above, 400 minus 16 times 1 squared. 1 squared is 1. 400 minus 16. H is 384. So our height is 384 feet. Well, that's not like too bad, but remember, that's only after 1 second. We've already dropped 16 feet. Okay, so then our ordered pair here is 1 comma 384. So why don't you pause the video and quickly fill in 2, 3, 4, and 5, and we'll check back in a second. Okay, let's see. So on 2, you found the total feet to be 336. And so that's 2 comma 336. For after 3 seconds, just after 3 seconds, we're going to be at 256 feet above the ground. So that's 256. Then after 4 seconds, you found this to be 144 feet above the ground. So 4 comma 144. And then just after 5 seconds, you guys were at 0 feet above the ground. which means we reached the ground already. 5, 0. So 5 seconds. 1, 2, 3, 4, 5. And we dropped 400 feet. And your stomach's up there. So let's take a look. We're going to graph these ordered pairs. So noticing our axes are already labeled for us, our height above the ground in feet and our time in seconds. Notice time in seconds is on the x-axis because it's independent, and the height above the ground is dependent. So the height above the ground depends on how many seconds we've been falling in this roller coaster. Ugh. Okay, so let's start at time 0 for the top, our vertex. We started at 400 feet. Then after 1 second, we're at 384. So notice this is 25, 50, 75, 100. So we're going by 25s. So if we're at 300 and we want to get to 384, we're going to go to 75 and just maybe a smidgen more. That's not too bad of a drop. That's doable. Okay. So then after 2 seconds, we need to go to 336. So we're going to go to 300, 25's here and 50's there. So it's kind of like in between 25 and 50. Not so sure about this. Okay. After 3 seconds, 256. So there's 200, 25, 50. So practically right. Oh, wow. That's dropping a little faster, you guys. And then after 4 seconds, we're at 144 feet, 100, 25, 50. It's below. Oh my gosh. Do you see how much farther we're dropping here in the same amount of time? Does that mean we're going faster? It does. We're going faster. And after 5 seconds, you guys, we reached the ground. Ooh. Okay, so I'm going to do my best to trace our trajectory. And we start to decrease faster and faster. And this is when I said, why did I do this? And notice this is just one side of the parabola. We can think about the other side if this was a complete parabola. Thinking about that. So after how many seconds does the steel dragon reach the bottom? 5 seconds. How do you know? At time t equals 5, the distance above ground is 0 feet. We have reached 0. So just in case you didn't realize how epically freaky this roller coaster would be, I got a video for you guys. So here you go. Little video courtesy of here we go. Bobsled. Psh. Anticipation. We're going up 400 feet. Here we go. We're almost at the top. Sure gets a while to get there. 5 seconds to reach the bottom, you guys. 5 seconds. Me neither. Don't like this. Whew. And just keeps going, you guys. So I don't know exactly when the largest drop is here. But obviously it's a pretty intense roller coaster. Hopefully you had some I just like I can't even watch. Can't even watch. Ah! Hopefully you've enjoyed watching this roller coaster. Whew, finally at the end. Thank goodness. Man. No, thank you. And he's laughing at the end. Okay. So back to our lesson here. Now that you saw a little bit of parabolic motion and a real world situation like a roller coaster, what we're going to do is some more math for the steel dragon. So we want to know about the velocity. So velocity is about speed and direction. So if we wanted to find the velocity of this roller coaster to figure out an average about like how deadly fast we were traveling, what we're going to find is the change in height over change in time. So remember, the change in height, that's your change in y, and change in t, that's your change in x. So there's another situation that has change in y over change in x, and that's when we calculate the slope. So if you take a looky-loo, if we were finding the slope, what we're finding here at each point of this curve is actually the velocity. So if we look at distance and time, this is the distance time, which is a speed. And then if we look at a first derivative of speed, we're going to get velocity, which is really cool. So what we're going to do here is we're going to find the change in height over change in time. So our change in height, to find the velocity, we take initial minus final. So our change in height, we started at 400 and we went all the way to 0. And then our change in time, well, we started at 0 seconds and we went all the way to 5 seconds here. So if we're looking at this, we can notice we're going to end up with a negative velocity. And that's because we're dropping this whole time. So remember, velocity is speed and direction. So 400 take away nada is 400. 0 take away 5 is negative 5. And that means that we have negative 80. So what does this tell us in our context? This tells us that the roller coaster drops at a velocity of 80 feet per second on average. Obviously, we can tell from our graph that we start off dropping and then we are dropping more as time increases. So we're decreasing at an increasing rate because we're going to continue going down, but every time we go down, every interval 1 second, we go down by more than we did before. Cool. So taking a look here, the equation that we use represents a quadratic function. And a quadratic function is a function that can be described by the equation in the form y equals a times the quantity of x minus h being squared, all plus k. In a quadratic function, the greatest power of the variable is 2, and the graph of a quadratic function is called a parabola or a parabola. And we've talked about that a couple of times, and notice there's a lot of similarities between our quadratic function and our absolute value function. And that's because they're going to interact very similarly, especially with this square. Kind of acts like that absolute value because anything inside these parentheses, once you square that value, is going to be positive. Very similar to absolute value, where the absolute value of any value is positive because it's a distance from 0. So really cool there, thinking about, what do you think K changes, or H and A. So they're going to control the same ideas, same thing, same motion, same transformations. So we're going to complete the table and graph we're going to complete the table and graph the given functions. So y equals x squared, this is our parent function. This is where we're always going to start, or we can call it our pre-image. So we're going to call this our parent function. You can also call it your pre-image. It's where you start. So here, if my input is 2, my output is 4. If my input is 1, my output is 1. If my input is 0, my output is 0. -1 quantity squared. Remember, when you input, you always use parentheses around your variable. So that would be -1 times -1, which is very different, remember, than just -1 being squared. This is positive, this would be negative. So just remember, you have to use your parentheses. They're powerful. That's why they're sideways muscles. Whoa. Okay, so 1 and 4. Again, very similar to absolute value, we have this beautiful symmetry happening in our table. 4, 1, 0, 1, 4. Note this is not a linear function. It's very far from a linear function. If we take a look at the first difference, 4 to 1, we're going to be subtracting 3. 1 to 0, subtracting 1, adding 1, and then adding 3, which shows you this is not a linear function. And then, because notice here we're changing by 1. But if we look at our second difference, -3 to -1, we're going to be adding 2. -1 to +1, we're adding 2, and 1 to 3, we're adding 2. Because we have a constant second difference, that is a huge telltale of that this is a quadratic function. Quadratic functions have constant second differences. So let's take a look at graphing this parent function, our pre-image. I'm going to start at 0, 0, because notice that is our vertex. It's where the symmetry stems from. And that's going to be really important for us to be identifying our vertex to be graphing. 1, 1, -1, 1, 2, 4, -2, 4. If we wanted to keep on graphing, if we inputted 3, your output would be 9, and -3, 9. And that's just going to make our graph look more accurate. We're going to try and make this look like it has some beautiful symmetry. Kind of makes this U shape. And remember, the shape of a graph is called a parabola, which you call it a parabola if you want to, just to help you remember how to spell it. Parabola, 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 parabola. Either one, doesn't matter. Okay, so now what we're going to do is we are going to transform our parent function. Notice we have a couple of things. We have this negative value, which would be a -a. Is that going to make a sad parabola or happy parabola? It might make a sad parabola. And then we also have this plus k here, and that is correlating to that plus 4. So think about, how is that going to translate? Is that going to affect the x direction horizontally or affect the y direction vertically? So let's take a look. A table of values is always a great place to go to see how is this function growing. If some people can put it in their heads, think, okay, as x increases, what's happening to y? As x decreases, what's happening to y? So let's take a look. And if you want to show a little bit of work down here, it's totally fine. Negative x being squared plus 4. So first I'm inputting 2. Again, I have to do my exponent first before I multiply, order of operations. 2 squared is 4 times negative, so we'd have -4 plus 4, which is going to get me 0 here. Okay, and then I'm going to take a look at 1. So -1 squared, all plus 4. 1 squared is 1. -1 plus 4 gets me 3. Okay, I'm going to input 0. 0 squared is 0. The opposite of 0 is still 0. All plus 4 is 4. -1 squared. Oh, do you think I'll have some symmetry here? Let's find out. -1 squared is 1. The opposite of 1 is -1, and -1 plus 4. -1 squared, 1. -1 plus 4, 3. Okay, and now let's take it the next one, negative 2. Negative 2 squared is 4. Opposite of 4 is negative 4. Negative 4 plus 4 is 0. So notice we do have some symmetry here. And taking a look, that means our vertex should be at 0, 4. And 0, 4 is a y-intercept. Your x is 0. So we're going to go up to 4. And then from here, we're going to go negative 1, 3, 1, 3, negative 2, 0, and 2, 0. So taking a look here, we have a sad parabola. It's sad because it was negative. And this plus 4 translated our parabola up 4. So I guess instead of saying a sad parabola, we should probably use like the mathematical term. So our parabola was flipped across the x-axis or turned upside down. It's opening downwards now. So the graphs are symmetric across which line? So symmetry means that line of symmetry. If I was going to fold this graph and this graph across and have it lay on the other side of it, it's symmetric across the y-axis. Oops. The y-axis, which you can call the line x equals 0. If they're asking you for like the equation of the line, they want to be very specific here and tell them exactly what they want. So explain in words how symmetry is shown in the table of values. So this symmetry in the table of values happens because of the quadratic function containing x squared. And because any number and its opposite when squared have the same output or the same value. So let's see, explain in words how symmetry is shown in the table of values. The quadratic function contains x squared and any value times itself is always positive. As well as any number and its opposite have the same square value. So because every number and its opposite is going to have the same output, every output corresponds to 2 inputs. And that's what's going to create that symmetry, except for the vertex, of course. So why does the symmetry occur? Explain using the equations. Oh, I guess I kind of swapped these, you guys. So explain how the table values the symmetry. The y values repeat. So that's how there's symmetry in the table of values. I'm sorry, I should have read that question better. So in the table of values, the y values repeat, and then using the equation, it's all because of that x squared. Okay, so explain in words how the graph, we graphed the red graph, compares to our parent function, and why did these changes occur? So we said that it's a sad parabola, so we can say opens downward or reflected across x-axis, negative x squared makes all outputs opposite. Or negative. from y equals x squared. And then we notice that we translated up. And we notice that we translated up exactly 4 units. 4 units from y equals x squared. And that's because of the plus 4 making all outputs shift up 4. So very similar again, almost exactly the same as absolute value. Okay, let's keep going. So now without graphing, we're going to make a prediction. So now we're going to be looking at y equals 1/2 x squared all minus 3. So how do we think this is going to be different? Well, let's first take a look at this 1/2, or kind of like this a value. We're not going to talk about that they're both opening upwards or both a happy parabola, because we're talking about how they're going to be different. But you notice that that a value is a half. So is it going to grow faster and be super narrow, or is it going to go slower and be wider? So you're right. I think it's going to grow slower, which we can also say as being less steep. You could say wider. And I think that's because of the 1/2 x being squared. And then I'm going to say translate down 3 units. I think that's because of the minus 3 at the end, that k value. So let's take a look. We're going to complete these tables and graphs. So why don't you take a moment and pause me and fill in these tables and graphs and check back in when you're done, and we'll see how you did. Okay, let's see how we are doing. So taking a look here, we had 2 squared. 2 squared was 4. Half of 4 is 2. And 2 take away 3, -1. 1 squared is 1. And then we have times a half, which is a half. A half minus 3 is -2.5. 0 take away 3 is -3. -1 squared is 1. 1 times a half is a half. A half minus 3 is -2.5. And here we have -2 again. And notice I see some symmetry, -1. And that's because here is going to be our vertex. So thinking about this, 0, -3. I'm pretty happy with my vertex being here, because since I said this -3 is going to translate the whole entire parabola down 3 units. So then 1, -2.5 is between -2 and -3. -1, -2.5 between -2 and -3. And again, I'm pretty happy with this because I know that my parent function parabola kind of grows a little bit faster up. And then let's do our last one, 2, -1, -2, -1. So notice we're growing slightly slower. We're going to be a little bit wider. Ooh, I like how I made that curve. It's really good. And we want to really try to make these look more of a U shape than a V shape. Something I want you to think about, if I gave you this table and the X values were blank, I probably wouldn't use 2, 1, 0, -1, -2, because it doesn't give me the best values. If I was going to choose which values to use for X, I'd probably go ahead and use 4, 2, 0, -2, and -4. And the reason for that is because I notice I'm going to be multiplying by a half or dividing by 2. So I want to put values that are going to be even. So if I take a look here and I use these numbers, the only different ones are -4 and 4. So 4 squared is 16, half 16 is 8, and 8 minus 3 is 5. So I'm going to have 5 and 5 here, which is actually going to give me a really good picture of how this graph is growing a little bit better. So if you ever need to add a couple more data points, or if you want to pick some different inputs to give yourself a better picture, go ahead and do that. Okay, so let's take a look at our next function we're given. Y equals 3 times x squared all plus 1. So this one's different, and let's think about what this is going to look like before we graph it. So we have this plus 1. It's on the outside. It's just affecting that y direction, just vertical. So we're going to translate up 1 from our parent function, which remember is y equals x squared. Okay, so I'm pretty sure that my vertex then is going to be 0, 1, because it's your y-intercept, your x is 0. So I'm thinking that this is going to be a 1. Interesting. Now, this 3 here, is that going to make my parabola grow faster and be narrower, or slower and be wider? So this doesn't actually make it grow faster. So it should be much narrower than this parabola, because it's going to be even narrower than our parent function. So taking a look, I'm going to have 2 squared is 4. 4 times 3 is 12. 12 plus 1 is 13. Wow, not even on my graph it's growing so fast. Let's take a look at 1. 1 squared is 1. 1 times 3 is 3. 3 plus 1 is 4. Negative 1 squared is 1. 1 times 3 is 3. 3 plus 1 is 4. Negative 2 squared is 4. 4 times 3 is 12. 12 plus 1 is 13. Okay, so we have 0, 1. Just like I said we would. 0 squared is 0. 0 times 3 is 0. And 0 plus 1 is 1. And then we went up to 1, 4, negative 1, 4, and if we're at negative 2, I mean, there's 10, 11, 12, 13. Oh my goodness. It just grew so fast. Wowzers! Look at that rapidly growing parabola. Quadratic. I hope that your parabola doesn't look as wonky as mine. Oh my gosh, Mrs. Barr. You need to get it under control here. Okay, so that looks slightly better. Okay, so we're going to complete each of these tables of values for each function, and we're going to graph the function on the same coordinate plane and label each graph as linear, absolute, or quadratic. So we're kind of bringing it all together for the past couple lessons, and taking a look, we are going to be able to tell already which one's going to be linear, which one's going to be absolute value, and which one's going to be quadratic. So the quadratic one is always going to be the one with the x squared. So this one's going to be quadratic. The linear one is going to be the one that has x and y all raised to the first power. No variables are being divided and no functions are being applied. So that's this one. It can be written in the form y equals mx plus b if we wanted to rewrite it. And then this is absolute value because, well, it has an absolute value function in it. Look at those bars. So nice. What nice bars. Okay, so what we're going to do is we're going to pause video bar. You're going to fill in these tables and do that graph, and we'll check in with you in a second. Okay, so this linear function, let's see. He says negative 6, 2, 6, 10, and 14. So if I go ahead and graph this, I'm at 4, negative 6, 2, 2, 1, 6, 0, 10. Looks like I'm going up 1, 2, 3, 4, and over 1. 1, 2, 3, 4 over 1. So I should go 1, 2, 3, 4 over 1. Perfect. 1, 2, 3, 4 over 1. Since they skipped 3, I'm going to use a tool to quickly graph this. There we go. That's our linear function, which is 4x plus y is equal to 10. Now I'm going to move on to my quadratic, and I think we should have gotten 3, 6, 7, 6, and 3. And we're like, oh, there's a vertex. 3, 6, 6, 3, 0, 7. Yep, there's a vertex. And maybe you already noticed, well, of course it's going to be at 0, 7, Mrs. Barr. We're adding 7 here. Well, now let me ask you, is this going to be a happy parabola or a sad parabola? It's going to be a sad parabola. So here I'm going to start at 0, 7. Then I'm going to go 1, 6. Oh, interesting, intersecting the line. Negative 1, 6. Negative 2, 3. And 2, 3. Almost intersecting that red line, but not quite. Remember, this is a parabola, so it should look kind of curvy. Maybe you're like, ooh, I really wish there was like a 3 value, just so I had a better picture of this to graph this best as I can, to be the best me possible. So think about that. 3 squared is 9, negative 9. Negative 9 plus 7 is going to get you to negative 2. Okay, so 3, 2, and that looks good. 3, 2. Interesting, intersecting that line twice. Okay, so we have these nice curves of the parabola. Notice it's never going to get exactly vertical. It's going to look really close to it. This is y equals negative x squared all plus 7. Negative, opening downwards, plus 7, translating from the vertex 0, 0 all the way up to 0, 7. Make that a little darker for you. Just notice the camera didn't pick it up as well. And then the absolute value, I believe you guys got 12, 6, 3, 6, and 12. And you're like, oh my gosh, symmetry in the table. You're seeing a beautiful vertex. And I always like identifying my vertex because it really helps me be able to graph accurately. And then double check I did the math right with my equation. So taking a look at the equation, we're adding 3 at the end, which is going to translate that vertex vertically up 3. And that 3 there should make us grow faster, narrower. And we're facing upward because that's a positive 3. So we have 0, 3, negative 1, 6. Ooh, intersecting both the other functions there. Negative 3, zoom up to 12. 3, zoom up to 12. Since I know these are 2 lines with opposite slopes, I can go ahead and grab my straight edge. And this is y equals 3 times quantity of absolute value of x all plus 3. Did you miss my singing? Maybe not. Well, you're getting some today. So taking a look here, state the point of intersection. Well, state the point of intersection means it's the one point that intersects all 3 functions. And that is going to be right there, my friends, at, let's see if I've got a 1, 6. 1, 6. 1, 6. Maybe I should use a different color because I already used yellow for my vertex. Here we go. 1, 6. 1, 6. 1, 6. Graphically, boom, right there. 1, 6. State the point of intersection, 1, 6. So now part B asks us to verify algebraically that your point of intersection is correct. Well, how can we verify that a point lies on a graph? That means we're going to substitute in 1 for x and 6 for y into each one of these functions, and we should get a true statement, just like in module 4. So we're going to do that. To verify algebraically, you have to use the algebraic equation. So I'm going to use 4x plus y is equal to 10. And here, again, I'm going to substitute in 1 for x and 6 for y and see if I get a true statement. Order of operations, 4 times 1 is 4. 4 plus 6 is 10. 10 equals 10. Woohoo! 1, 6 lies on the line. Let's take a look at our parabola, our quadratic function. Remember, parabolas and quadratic functions have an x squared in them. So we have y equals negative x being squared all plus 7. 6 equals negative, here's my parentheses, 1 being squared all plus 7. Well, 1 squared is 1, the opposite of 1 is negative 1, and negative 1 plus 7 is 6. 6 equals 6, woohoo! That point also lies on our parabola. Last one we have to check is our absolute value function to verify all 3. Remember, if it only lies on 2, like negative 1, 6, it will only make these 2 functions true, the parabola and my absolute value, but I want a point that lies on all three of my functions here. Super fun. Y equals 3 times the absolute value of x all plus 3. Y is 6, x is 1. Ooh, absolute value of 1 looks kind of funny, huh? Maybe we'll make it look more 1-ish. Plus 3. Absolute value of 1 is 1. 1 times 3 is 3. 3 plus 3 is? Hey, it's 6. So we have now verified algebraically that the point 1, 6 lies on all three of those functions. You're also able to know which one's linear, absolute value, and quadratic by looking at the equations. We could figure that out by looking at the table of values or by the graphs. So if I was just given the table of values, I would try to see about their first and second difference. So obviously, if we look at our linear equation, we're going to have a constant first difference. So we can write that, constant first difference. If we take a look at our quadratic, you're going to have a constant second difference. Constant second difference. And for our absolute value, you'll notice that your first difference is a number and its opposite. So you'll see that you have like the slope here of this line is negative 3. 1, 2, 3 over 1. 1, 2, 3 over 1. So this slope's negative 3. This slope's positive 3. So you'll notice that in your first difference as well. So cool. That concludes our 7.2b quadratic functions dealing with parabolas. We're going to be working on part 2 of quadratic functions next. And when you're out in the real world, maybe go bounce a bouncy ball and take a look at that parabolic motion as it keeps bouncing. Enjoy, mini mathematicians. Do your best. Be nice to everyone. Video bar out.